It is my great pleasure to introduce, let's see how well I do this, Dr. Coskun Cetinkaya. Pretty good, huh?
Yeah,
pretty good. I learned it like 30 seconds ago. He's an associate professor in engineering here at SUNY Poly, and he's going to talk about multi-channel cooperative MAC protocol for wireless LANs on Mars and Saturn. Is that what I just heard you say? Yeah. Take it away.
Thanks. Hello, everyone. I'll try to make it quick, hopefully.
No.
So first of all, before I start the topic, let me just give you brief information about what I'm doing, what are my interests. My research is in general wired and wireless networks. Currently, I am working on multi-channel Adhoc networks. The reason I am working on this problem more is because I have been interested with some of the project with the Army, so that's why that's become more important for me. But in general, I am working on Adhoc and sensor network, coordinated radio, and I have an interest to move more toward the network security coming years. Expertise, algorithm design, mathematical analysis, quality of service, MAC layer design. So, what's MAC layer? MAC is actually short for the medium access control. Most of the problem, for example, anytime you have an open spaces, usually when you transmit something, it's a broadcast network. When it's a broadcast network, that means if more than one transmission done, then they will collide. So to make sure that there is an efficient use of the air or spectrum, you have to have some kind of rules set for the people to talk. For example, think about a debate, regular debate. What happens? There's a moderator sits down and address each one. Or people try to ask a question to the president or somebody there, coordinate who's going to ask question next, right? Why, if you let it, everybody fly, then it's become a chaos, right? Like if two people start fighting each other, you don't hear what they are saying because they are all shouting, they are trying to push themselves down. So there must be some kind of a control rule. So what are the control rules in general? There are two types of control rules you can put. One is a coordinated. In the coordinated, you usually assume there's a master or somebody allows who is going to speak next. In a debate, that will be a moderator. If presidential news conference, somebody from president's staff will point out who is going to ask, or president himself can point it out. In the wireless networks, like most of the cellular technology, we have a control access. They have the same problem. But we have a cellular tower, identify each user, when they are going to speak, and how long it will take, and which spectrum they are going to utilize. That's good. But what happens if there is no infrastructure or there is a master is not possible? In that case, you have to some kind of random rule, but within some reasonable rule, people try to talk. For example, think about a social conversation. What happens when two people speaks? They will collide, right? Then, depending on who is more kind, will let the other person to speak. Right? Then, but everybody else around there knows that if Deb and I talked at the same time, I let Deb talk first, everybody else around us knows that I have something to say, right? They will wait until I say something that somebody else will jump. So it is random access. There is no written rule, but it's a social rule we put in place. For in the wireless network, there is the cases. We will call this a collision resolution. In other words, if more than one people speak at the same time, how are you going to resolve this conflict? Or we will say, in MAC term, we say collision. Okay. So what are the applicability? Think about an army operation. You have a drone or unmanned vehicles or regular flight flying around. Then soldiers operating tanks and so on and so on. You have to provide some kind of communication among all these without any infrastructure. So that's the main problem we are addressing. Okay, again, most of the time, Adhoc Network is the Army's main interest, and the paper come up with the Army proposal is still pending, hopefully get it done. So the whole idea is, if you are close by multiple users, each one has its own peer to talk, but if you have everybody use the same spectrum, if one communication going through, then the other has to be silent to make sure that that communication happens successfully. For the connectivity problem, Army or Adhoc Network assume everybody is on the same channel, although multiple orthogonal channel available. What's orthogonal channel? Basically, Deb and I can speak on the channel 1, another peer can speak on the channel 2, another peer can speak on the channel 3. So you can have, if you have a 3-channel orthogonal without interfering each other, then you can actually at the same time 3 communication going through. That means 3 times more capacity. That's the whole purpose. And this is the simple case. This is 1 channel versus 13 channel. So you can have a 10 megabit link versus 120 megabit. So there's a huge gain, right? But as we know that if there's a gain, there's some loss, right? What's the problem? How are we going to explore all these available channels? First of all, 2 people, 2 devices can be on the same distance, same room. But if I'm operating in channel 1 and John is on channel 2, we cannot communicate. First of all, if I have a packet to send somebody, I have to first find out where that person is or their device is. Okay? That's the main problem. Finding the receiver. Then, how are we going to schedule the transmission? After I found it, I have to stay on the same channel. Should I stay on the same channel, or are we going to change the channel based on what route? That's the second. Third, if you have, let's say, 3 channels, but everybody end up being on the first channel, that's not a good solution. Basically, you want to distribute every user close to equal to each channel. So that's the third problem. So anytime you design a MAC layer, then you have to answer all these 3 major questions. Okay? So what are the solutions out there? Number 1, and the oldest one, is called dedicated control channel protocol. This is easy. What you do, if you have, let's say, 13 channel, you dedicate channel 1 as a control channel. Then you say, anytime you have a packet to transmit, you come to the control channel and find your peer there. Then choose one of the available channel and go there and make the transmission and come back. That's a really good solution if you have a commercial drive, like a commercial interest, because the control channel you can secure for some reason, but it is not that secure, because wireless networks, you can jam a channel and take down whole communication. So that's why it's not a good interest for army or military application, but the commercial application is a good solution. But most of these devices, there are actually, for this type of solution, there are 2 types of solution. Number 1, basically you assume multiple transmitter and receiver. In that case, you can stay one transmitter at the control channel and one you can make a transmission on the other channel. That way you have a knowledge of what's going on every single time. But most of the device is not there. Have the 2. Usually you have only 1 channel, 1 device to transmit or receive. Second, those solution is not a fault tolerant, especially if military communication or commercial. What if if I require only 2, always have 2 transmitters, what happens when one goes down? So my whole information is gone, right? So then if you have a single transmitter and receiver, what happens when you move to another channel to make a communication? When you come back, you have no idea what's going on. You don't know which channel is available, which channel is in use. That's the main thing. When you schedule, you want to schedule a channel is unused, right? But if you are gone for a certain time period, when you come back, you lost the knowledge of information about the channels. So that's the problem of this approach. Second is people says, okay, for that problem, eliminate that problem. Let's assume rather than dedicated channel, still we have a dedicated channel, but everybody comes to dedicated channel for a certain time frame, then everybody make the arrangement, then we go transmission mode. Then after a while we will come back and make the arrangement and go back. It's a good approach, but the main problem of this one is the synchronization problem. So you require every user to synchronize each other. And it's a hard problem in the wireless networks. Third one is basically called common hopping. If you have a 3-channel, you stay in the channel 1, make the arrangements. If somebody makes an arrangement, everybody else will move to the next one. And everybody one person make an arrangement there. As soon as there is an arrangement to transmit, everybody moves to the next one. The main problem of this one is if the number of channels is small, you wrap up. So that's the main issue. Still also a synchronization is required. So it's not. This fourth one is my proposal about the Army. I'm not going to talk about that much in this. Is basically making a synchronized decision. Every user for themselves, but you put enough rule that receiver and the sender will be in the same channel same time, sometime. It could be within a second, it could be within a minute, but you make sure that they come back to each other, see each other sometime in period. And you want to be bounded time frame for that. So, today's talk is we are going to talk about the dedicated control channel problem, and we assume single transmitter and receiver, okay? For that reason, we assume n+1 channel, and we dedicate the channel 0 as a control channel, and the other n channel is data channel. So they will be the regular data transmission. And for that reason, we assume that in order to make a transmission, you come to the control channel, make the arrangement, and find one free channel, and go there, make the transmission, data transmission, and come back. Okay? That's the requirement. So again, we are using half duplex. That means you can transmit, but you cannot hear it. That's the common, like if you have a wireless router or wireless transmitter, that's the way. You only have a half duplex. In other words, you can transmit or receive, not do both at the same time. But the problem for this, 3 questions you have to answer. When to start reservation? You make sure that the reservation happens before the channel becomes free. So you can utilize that channel. Then, if you come back, how do you obtain the channel status? How do you know which channel will be free for the next transmission? Also, let's say I make an arrangement with the talk with the dad, go to channel 2. When I come back, I want to talk to John. How do I know John is in the control channel, or is he transmitting with somebody else on another channel? So that's another problem you have to answer this kind of question. So let's start the first one. When to start? If you are naive, let's say I'm intending to make a transmission at the channel I. If you wait, the channel becomes free. This is the free time. Then you start transmission. Transmission take time. Reservation take time. So during this reservation, the channel is idle. So that means you are not utilizing. This is a very naive solution. Ideal case is you want to make sure that you make the reservation, and when you switch, channel become available immediately. That means you can transmit whenever you switch. That's the best case. But in this case, you have to know a perfect knowledge, and it's not possible. Our solution, what we are trying to do is, we try to start such a way that this is the actually unknown parameter, and you want to make sure that this unknown is minimized, so that the time idle duration on the data channel is minimized, and you have achieved the highest throughput. And for that reason, we says you start the transmission of any channel, reservation channel, when channel become idle minus switching time and full reservation circle. Okay? That's number 1 question. Number 2, how do you know when you come back which channel is available? There are a couple of techniques. People says one of the solutions out there, it says, okay, since your neighbor knows which channel is available, you try, let's say I try channel 2, when I transmit channel 2, when everybody hears that I'm trying to schedule a channel 2 and they know channel 2 isn't busy, they interfere. That way you cannot schedule something. Very expensive solution in terms of throughput, sorry. The second one, you allow user to transmit additional information. When they schedule, they send all the channel availability, and you know which channel will be available with what time. So you know that. And the requirement for you is to wait until one person transmit before you. That way, the first transmission, you have the whole picture of the network. It's a good solution, but expensive in terms of, because these are the control data. That means basically any additional information you send, you are taking away from the useful information. So our goal, our solution is adopt this one. But rather than if you have a 13 channel available, then you transmit information for each channel. Each channel requires 4 bytes, they're very expensive. We said, okay, rather than doing all 13 channels, just let me know 2 channels. The one you are scheduling and the one next available. So that way, our case is good. Second, what if, let's say you have a 3 channel and only 3 users. So when you come back and wait somebody to transmit, it may never happen. So for that reason, we say, okay, when you come back, you set the channel availability maximum time a channel can be used. If nobody transmits within that, that means that channel is available. So that's an assumption. It worked very well. But spare case, it is very unlikely cases because most of the network we are interested in is a very dense network rather than a spare. But you have to solve that problem in case the number of users is very small. Also, we require we call user now. In other words, whenever I hear John make a reservation on a channel and I have a packet to go to John, then I will wait, set up a timer, so make sure that John goes to the other channel, make the transmission and come back. Then I know John's in the control channel, so I can make a reservation. That's the third problem. Actually, I'm not going to go whole idea. This paper is published in Elsevier Adhoc Network in May issue. So there are actually 7 steps. Whole idea is basically, let's walk through. First, you identify when the channel available. Then you start transmission, but there will be a collision because it's a random access. After you reserve this channel, then you go to the switch, and when you go to make the switch, then you make a transmission and come back and apply this again. Of course, since I'm kind of interested in the math, it's a random access, it's a probabilistic access. That means anytime you do some decision, you have to make a mathematical model to make sure that your decision making is efficient. For that reason, we assume that if you know the number of users in the system, and it is actually easy to estimate, then you can have actually a probabilistic method to minimize the reservation duration. And for our cases, we had 2 parameters, omega c and omega s, and we run this project, this probabilistic method, and find the optimal solution, optimal pair of omega s and omega c. But there are cases you cannot predict or estimate number of users. In that cases, we use a minimum mean square error estimation, assuming that you bulkly know how many users in the system, maybe 10 to 100, then you find that pair overall, it provides you the best solution, any given number of users. Okay? If you are interested, I can give you the detail of this. So, luckily, we show that our mathematical model captures actual behavior of the network. And we found that the parameter we choose is both in analytical model and the simulation model gives the best results. That's the good news for us. And in this case, for example, this is actually analytical solution. This is actually simulation solution. And this is also, I provide here, minimum mean square error estimation. In this case, we assume we have a 1 to 600 user for minimum estimation. This is the period. As you expect, when number of users is small, you wait longer. That's why throughput goes down. When you go higher number of users, then the collision gets higher, so throughput goes down. But as you can see, except that this is the spare mode, because there are 13 channels, this is number of users is more than 13. Optimal solution is actually if you can estimate number of users, it's a steady throughput. That's a very good solution. Okay? Then we said, let's see if our protocols compare with the current one to DCA and MMP is the current solutions. How it works in terms of if I increase the number of channels. I said this is actually single channel solution. This is multi-channel optimal solution. Basically what we are saying is this is the best you can get. Any given scenario. This is the best solution, this is the worst solution. And your solution somehow lies in between, right? And you expect that if number of users, the channel is increasing, throughput linearly should increase. Even though you may not reach the optimal solution, but it should be close. What we found out is basically, this is the current available solution. When you increase number of users to 7 or channel is more than 7, throughput stays the same. And our solution do better. I was happy with it. But mine also had a problem. When I reached the 9 channel, even though I increased, don't forget, current technology allows you to have the 13 channel. But mine stuck at 9. Then the problem is, why this happened? Right? First of all, the easy answer is control channel become bottleneck. In other words, you cannot schedule fast enough so that the channel become idle, sit there because you cannot schedule fast enough. Then the question is, and we look at the throughput, mathematical model for the throughput, it depends on the packet size and the reservation. And this is actually packet size, for this is the data rate, and this is number of channels you can support. Whole idea is actually, it definitely depends on the packet size. When you increase the packet size, throughput increases. But when you increase the rate, you expect the throughput increase significantly, but it remains the same because number of channels each protocol can support gets smaller. So it is steady. It depends on packet size, but not the rate. So that's a very bad thing. Then I look at the mathematical model and I said, why this is happening? Because all the protocol assume you can transmit 1 packet per reservation. And if you use a 1 packet reservation, you cannot schedule fast enough. So that means when you reserve a channel, you have to make sure that your channel duration is more than scheduling decision. And we changed our protocol, we call NCMP plus, because we make a requirement of number of packet change higher. And this is the solution we have. So as you can see, as packet size increases, throughput increases. Also, data rate increases, throughput increases as well. How do we achieve? For example, if you have a 500 packet, size packet, and data rate is 6, you need to send 3 packets to, whenever you make a reservation, you have to send at least 3 packets. But you increase the rate to 54, you have to send 9 packets per reservation. And as you can see, with this you can have 60 megabit versus 263 megabit per second. That's how much you can increase. And when the packet size increases, you can go all the way to 400 megabit per second. And we see that, again, these are the solution, early solution, single packet. When we allow a multiple packet transmission, as you can see, our protocol keep going as a linear of the number of channels. And again, we look at all the cases, number of users, high or low, different packet sizes, and we found that our protocol provides high throughput that's desired, load, balanced load. We look at the utilization of individual channel, and we see that they are very close to each other. That's one of the goals. And we want to do this in a very low overhead, and we achieve by doing this. Actually, this is the first one. I can go through more detail, but that's the first part of the talk. Yes? John.
So the reservations, your reservation packet has an information on just 2 channels?
2 channels.
Have you explored using a third?
It doesn't necessarily. We see that we look at the 2, 3, 4. Basically, you want to make it a minimum. 2 and 3 has almost no difference, because the protocol we are utilizing is a fair protocol, short-term fair. In other words, everybody gets equal chance to transmit at any given time. For that reason, what you need to transmit is the channel you are aiming at the next channel available. Because if you come back, you know that which channel they are reserving, and you know the next channel available, so you shoot for that one.
So your control channel knows which one to tell you about.
If somebody is on the control channel long enough,
yeah,
will capture every single information about each channel. But for when you come back, all you need is the next available channel.
Okay.
If somebody else transmits before you, then second channel information on the second reservation, you go to the third channel. So having only two channel information is good enough. Again, come back to the first problem. We use a dedicated control channel. But when you have a military operation or highly time-critical information, it's not a good solution. Because when you dedicate the control channel, somebody comes there and jam that channel, then whole network goes down. So for that reason, you have to have a distributed solution. And the first approach does not allow you to have a distributed solution.
That's one of the paradigms in military, that you have to have a distributed solution.
Yes. For that reason, how are you going to solve this problem? And that's actually, I'm lucky to finish up the paper soon. So we had a different solution. In that case, everybody acts randomly, but we make sure that each user find each other within a 10 milliseconds. That's a very good solution. Basically, if you have a packet, I can guarantee that within 10 milliseconds, you can find your peer and start transmission. And for this reason, whole idea is basically we separate user into 2 groups. One is called search user. Second group is the regular user. Search user, let's say you have a 13 channel. It's like a thing about the clock, indicator for clock and the minutes, right? Within an hour, they will be synchronized, right? You guarantee that within any hour, they will be synchronized one time at a time. But if you look at the clock indicator, hour indicator, it moves very slowly versus minute indicator that goes 60 times faster, right? That's the idea came to me. Can we, if you are searching, can you go fast, search fast enough? If a data user stays in channel 1, you come back and make sure that you are in channel 1 before it's switched. We found that it's very hard to do, and we require actually the duration of the data channel twice the number of channels available. So that way, we make sure that they get to each other. That's actually 12 milliseconds comes into, because individual data user must stay in any channel 12 milliseconds. In that cases, searching user can come back and find that person. So we distinguish 2 types of user. One moves slower, other goes faster, so they will get together on the same channel in some time. And actually, in this case, we have actually, this is the best solution you can get with the number of users per channel. And this is our solution. Actually, we found that within 5%, our solution gets the detail. But this is the problem I sent to the army and hope this is actually a single channel solution. That's the worst you can do. This is the best you can do. This is the worst you can. And we found that our user algorithm works close to the best solution. Of course, we assume the number of users is 10 or more. And spare mode problem is the same remain because searching time takes time and throughput is not utilized if number of users is based on that.
It's a 10 meg channel?
This is actually,
So
no, 2 megabit per channel, but this is actually 3 channel. Each channel has a 2 megabit per second.
2.
Yes, that's why this is, but you can, as you know that the throughput, packet size is very small. You cannot achieve 100% utilization no matter what. So, how do we extend? This is actually kind of an overview of my army proposal. I can talk about this more detail if you need it. But, okay, what we propose in one solution is a local solution. In other words, everybody is an approximate distance of each other transmission. What happens if I need to send a packet to the Andrea, but I cannot transmit directly? So Adhoc Network, what you assume, you have another relay. Somebody else will forward. So I will send the dev, and that will forward to her. Then that
We got it covered.
brings a whole new dimension of the problem. First of all, how would you find the route? How would you design a transmission? Because since for the local, when I send a packet to that will send me an acknowledgement saying that, okay, I got your packet, reservation, right? But if it's a multi-hub, how do I make sure that the packet goes to the destination? So again, if you bring this single local problem into the global problem, it's become a major issue. That's why what we sent to Army is, if the device is heterogeneous, there is also mobility. Everybody moves around. That's the Army's interest. And there are many users in a multi-hub scenario. We try to scale our solution as a local solution to the global solution. That's the proposal. Of course, this approach you can also do a sensor network solution. That's problem is similar, but then you have an energy reservation requirement, energy conversion, because you don't want to overburden it. If you, especially in military application, you put that sensor somewhere, you want to make sure that that stays long time. You don't want to go back and redo the sensor. So that's another issue. If there's a power issue and you want to make it more efficient, sleep and wake up period, those kind of things. So that's another problem. Then also the mesh network is also interested on the same problem. Again, mesh network also use a little bit better solution because there is no power requirement and there is also kind of infrastructure. But it's still single channel versus multi-channel problem. You can extend to the depth as well. Again, we can extend 3 different areas of the same problem. Actually, I don't know if I went too fast or what. I'm done. If any question. You told me I should be done by 1 hour.